Thank you very much for giving me the opportunity to speak here. So I'm the last speaker, so please stay alive. What I'm just going to do is introduce quickly who we are. So we're a company based in Brittany, and we make this own design electronics that we implement in this type of systems, and then that we test some type of hydrophone cores that we can test database or different types of pressure systems. So yesterday I just met with Thomas from Oceanoise, and he just advised me that I was about to speak for a mapping session, and I was just okay. So I went on Google and went to see what was mapping, and I saw some of your papers, very interesting. And I tried to focus my speak to noise mapping. I realized that the main objective of modeling and mapping is that you have to cover a wide area and you have to model a broad type of sounds. And the model has to be as accurate as possible and closest to the reality of a changing environment. So it means that the model, as we have seen on all the presentation, have to be validated by in-situ measurements. So if we go to like a pyramid of needs to mapping and modeling, we've got the modeling on the top, which is all the algorithm taking a high number of parameters. Then you've got the in-situ measurements. But if you want reliable data from these in-situ measurements, then the base of everything is the reliable data coming from the measurement system itself. And so the real question is how to ensure to have quality calibrated measurement system to validate the model by in-situ measurements. So I'm just going back to the very basic of acoustics. So what we have in the beginning is a pressure level. Then you've got the hydrophone, which is giving the data into volts, and you've got the HD converter, which is digitizing the data. And this is this data, generally in wave format, that you're going to process to recover your pressure level. So what you have to calibrate and what you need reliable is not only the hydrophone, but the whole measuring chain, gathering the hydrophone and the digitization system. And generally, when we talk about modeling, we want to monitor the broad type of sound, so from low to high levels and from low to high frequencies. And so what we want to measure mainly is everything. But if you have a non-adapted system or non-adapted hydrophone, you can quickly lose the reliable data you're looking for. So I just like to make a small list of what can impact if you don't have the adapted system. For example, if your HD or your hydrophone is noisy, you can have a loss in your low frequency measurement, or you cannot record your low noise level. If you have a hydrophone too sensitive, that might clip when you have high level of noises, and you can have unexploitable data here. If your HD converter has a dynamic loss in the signal, so we talk about effective number of bits, you can have a loss also here, and you can lose sensitivity while you're recording. If your hydrophone is plugged to your recorder, you can have reflection or reverberation effects that you may think it's coming from the propagation model, but maybe it's coming from the reverberation. If the anti-aliasing filter is not efficient, you may have some strange data just rippling on your acquisition. If you have, it's quite depressing. If you use a numerical gain, it can give you the feeling that you have a really nice sensitivity, but the truth is you might lose a high level of noises measurement by just increasing the self-noise of the system. And if you have a system which is not resistant to what we call the blocking signal, let's imagine you've got a sonar which is speaking very loud at 40 kilohertz frequency. How may that affect my system, and will it still be able to record the other noises? And this is just to say, well, maybe your reliable data is just this small piece here. And so it's just to show you that there's some questions. Everybody knows to ask things about hydrophone itself and calibration, but you're also allowed to ask questions to the digitization system and the whole recording system. So just feel free to ask about the effective number of bits, the type of gain settings, the dynamic range. Also think about signal to noise ratio, which is not the dynamic, but it is the real level from low to high level that you can measure. You can ask about the high pass filter. Also try to find the good adapted hydrophone to the type of noise you measure. And if you have, for example, a system using two channels, one for high level, one for low level, think about the crosstalk between the channels. Meaning that if I record something on one channel, will that affect the other channel recording something else? And so this is what you can achieve, for example, now with a 24-bit system and a below system zero hydrophone, like a Brazil, for example. And you see that we're still cannot monitor everything. So you need at least a dual hydrophone if you want to monitor high level of noises. And combining the two, you can listen to everything. So, going back to the first question, how to ensure to have quality at that scale, calibrating measurement. So, it's one of the complicated tasks that has, for example, people in the bias project. How can I calibrate my system? One of the possibilities is test and calibration. It's interesting because you have emission source, you can make comparative models, you can have a broadband calibration from low to high frequency. The drawback of this measurement is that it is before your measurement or after your measurement, so that you cannot know how your recording system reacts in the water. Another measurement is piston phone calibration. So you have your piston phone, you have connected to your hydrophone, then to your recording system. And what you can do with our system, which is interesting, is you can upload both the calibration of the A to D converter and the calibration of the hydrophone, and visualize in real time from a laptop the peak of 250 Hz of your piston phone and check if the whole chain is fully calibrated. So the interesting thing is you can make an order field check of the whole chain. The drawback is still a single frequency check. So, going back to in-situ measurement, we see we've got different factors. We've got the spatial factors, so we need to measure at different locations, also with a search presentation. We've got the temporal factor, and we've got a multi-factor. We don't have only sound, we also have the conductivity, temperature. So we begin to think of how can we answer all these purposes. So we decide on the design of a small case, which is on the one hand a recording system calibrated with the possibility to listen while it's recording. You've got the GPS position for the spatial, and you have a total body gathering calibrated hydrophone, conductivity, pressure, temperature, and an emitting source. So the interest of having an emitting source calibrated is that if you have, for example, a recorder deployed for a long time, you can come above them and send different types of sure, impulse, or pre-programmed short sequence, or even you can play back your own wave files. So, developing the system, we realized that there were some operational requirements. One of them is the system has to be compact, and the other one is the budget. So, we ended up with a system, a very small case, avoiding to have a full CTD. We measure CT on the bottom, on the total body with the transducer, which is both emitting and receiving, and you can have the depth just with marking on the cable, and so allowing you to make different quick measurements position with the GPS. The drawback of this is obviously it cannot allow you to make high level of emission, so you cannot make a full propagation modeling, but it can already give you a known information sent to a calibrated level close to your recorder at a certain time and measure at the same time how is the sound profile at this T time. So it can also allow you, if you have a number of recorders deployed, to validate the recorded data. It could also be used as a synchronizer. And we're also thinking about an application like calibrating. There's a lot of CPODs, for example. And how can I calibrate? How can I check if they're still working great? So you can replay like dolphins emission or porpoise emission and check if these things are working. So this is another example of application for propagation measurement, but however still in the limitation of the transducer itself. So just to conclude, say that modeling mapper requires to... No, that's fine. That's okay. I think he's angry. So modeling and mapping requires to be validated by in-situ measurement, and industrial company, hardware and software, calibrated solutions exist, and we're always open to high-level brains on the science to improve the solutions to the science. So when we're here on the corridor, actually, we're not only selling, we're really interested to have people coming and share the ideas and help the science. And an example of these, I just added sediment profile. And this system we're currently working on is to look at the acoustic response of the sediment. So it could help you to know how is the telemetry inside the sediments compared to the water one at different localizations. So that's it from me. Thank you.
Thank you very much, and thank you, warmly thanks to all the contributors and the timing as well. So if there is, maybe before we start the discussion, some questions about the presentations.
Hi. Question for Christine. Oh.
Yeah, she's busy, so should take another question.
Christine.